Learn Preprocessing. Description. Explain in detail. Sci-Kit Learn's preprocessing module provides a set of tools for transforming raw data into a format suitable for machine learning algorithms. This is crucial as most algorithms assume that the input data is scaled, centered, and in a specific format. Inputs. Input 1. Explain in detail raw data, typically in the form of a NumPy array or pandas data frame, containing features and potentially labels. Input 2. Explain in detail parameters for specific preprocessing techniques. This can include values like scaling range, number of bins for discretization, etc., depending on the chosen method. Outputs. Output 1. Explain in detail transformed data, often in the same format as the input NumPy array or pandas data frame, but with features scaled, centered, or otherwise modified based on the applied preprocessing technique. Output 2. Explain in detail. In some cases, preprocessing methods may generate additional outputs like the calculated means, variances, or transformation parameters used. Steps. Step 1. Explain in detail data cleaning. Handle missing values, inconsistent data types, and outliers. This might involve imputation techniques, data type conversion, or outlier removal. Step 2. Explain in detail feature scaling. Normalize or standardize features to a common scale. This prevents features with larger magnitudes from dominating the learning process. Common techniques include min-max scaler, standard scaler, and robust scaler. Step 3. Explain in detail feature encoding. Convert categorical features into numerical representations that machine learning algorithms can understand. This involves techniques like one-hot encoding, label encoding, or ordinal encoding. Step 4. Explain in detail feature transformation. Apply nonlinear transformations to features to improve the model's performance. This might involve techniques like polynomial features, log transformations, or power transformations. Step 5. Explain in detail dimensionality reduction. Reduce the number of features while retaining as much information as possible. Techniques like principal component analysis (PCA), linear discriminant analysis (LDA), or feature selection methods can be employed. Metrics. Metric 1. Explain in detail model performance metrics. After applying preprocessing metrics like accuracy, precision, recall, F1 score, or AUC are used to evaluate the impact of preprocessing on the final model. Metric 2. Explain in detail metrics specific to the preprocessing technique. Some techniques have specific metrics to assess their effectiveness. For instance, PCA can be evaluated based on explained variance ratio or the number of components needed. Visualization plots. Visualization plot 1. Explain in detail scatter plots. Visualize the distribution of features before and after scaling to understand the impact of transformations. Visualization plot 2. Explain in detail histograms. Analyze the distribution of features before and after encoding or transformation to identify potential biases or outliers. Visualization plot 3. Explain in detail pair plots. Explore relationships between features and identify potential multicollinearity issues. Visualization plot 4. Explain in detail scree plots in PCA. Visualize the explained variance by each principal component to determine the optimal number of components to retain. Fine-tune parameters. Parameter 1. Explain in detail scaling range. Adjust the minimum and maximum values to which features are scaled, e.g., min-max scaler. Parameter 2. Explain in detail number of components in dimensionality reduction methods. Specify the number of principal components or features to retain. Parameter 3. Explain in detail encoding strategy. Choose between different encoding techniques. Based on the nature of categorical features. Uncertainty methods. Uncertainty method 1. Explain in detail. Bootstrap resampling. Generate multiple datasets by resampling the original data with replacement and perform preprocessing on each resampled dataset. This helps assess the variability in the transformed data due to randomness in the original dataset. Uncertainty method 2. Explain in detail. Cross-validation. Split the data into multiple folds and apply preprocessing to each fold separately. This allows evaluating the robustness of the preprocessing method to different data splits. Challenges and fixes. Challenge 1. Explain in detail data leakage. Preprocessing using information from the target variable, e.g., scaling using the mean and standard deviation of the entire dataset including the training and test sets, can lead to data leakage. This results in an overly optimistic model performance on the test set, as the model has learned from information that is not available in real-world scenarios. Sample use case that resulted in challenge 1. Using standard scaler on the entire dataset before splitting into training and test sets. Fixes to challenge 1. Fit the scaler only on the training data and apply the fitted scaler to transform both the training and test data. Challenge 2. Explain in detail overfitting. Applying overly complex preprocessing techniques, especially dimensionality reduction methods, can lead to overfitting. The model might learn the noise in the training data, resulting in poor generalization to unseen data. Sample use case that resulted in challenge 2. Using PCA with a very high number of components, leading to the model learning intricate details from the training data that might not be relevant to the underlying pattern. Fixes to challenge 2. Use cross-validation to select the optimal number of components or features to retain. Consider simpler preprocessing methods, and monitor the model's performance on a holdout set to identify overfitting. Challenge 3. Explain in detail handling categorical features. Directly applying numerical preprocessing techniques to categorical features can lead to misleading results. Categorical features require specific encoding techniques to be properly handled. Sample use case that resulted in challenge 3. Scaling a categorical feature like gender using min-max scaler can result in incorrect interpretations, as gender is not a continuous variable. Fixes to challenge 3. Use appropriate encoding techniques like one-hot encoding or label encoding to convert categorical features into numerical representations suitable for machine learning algorithms. Challenge 4. Explain in detail inconsistent preprocessing. Applying different preprocessing methods to different parts of the data pipeline can lead to inconsistent results and make it challenging to interpret the model's predictions. Sample use case that resulted in challenge 4. Applying standard scaler to features used in a linear model, but not to features used in a decision tree model, can result in inconsistent scaling across the pipeline. Fixes to challenge 4. Standardize the preprocessing pipeline, applying the same methods to all parts of the data processing flow, including features used for different models. sklearn preprocessing binarizer. Description. The binarizer class in Sci-Kit sklearn is a data preprocessing technique used to transform numerical features into binary values 0 or 1 based on a user-defined threshold. This is particularly useful for binary classification problems where a feature is considered present or absent based on its value relative to the threshold. Inputs: X, a NumPy array or pandas data frame containing the numerical features that need to be binarized. Threshold, a float value defining the threshold for binarization. If a feature value is greater than or equal to the threshold, it is converted to 1, otherwise it is converted to 0. By default, the threshold is 0.0. Outputs. Transformed X, a NumPy array or pandas data frame containing the binarized features. Self, the binarizer object itself, allowing for reuse of the same transformation on different datasets. Steps. Data initialization. The binarizer object is initialized with the desired threshold value. Feature transformation. The binarizer transform method is applied to the input data X. Each feature value is compared to the threshold, and a binary value 0 or 1 is assigned based on the comparison. Metrics. Accuracy evaluates the performance of a classification model on the binarized data. Precision and recall measure the model's ability to correctly identify positive and negative instances. Visualization plots. Scatter plots visualizing the distribution of the binarized features to understand the impact of the transformation. Histograms illustrating the frequency of 0 and 1 values after binarization. Fine-tune parameters. Threshold. Adjust the threshold to control the binarization point. A higher threshold results in fewer features being classified as 1. Uncertainty methods. Confidence intervals estimating the uncertainty associated with the threshold selection. Cross-validation evaluating the performance of the binarizer with different thresholds using cross-validation. Challenges and fixes. Challenge 1, choosing an appropriate threshold. Sample use case that resulted in challenge 1, a dataset with a highly skewed distribution of values might require careful selection of the threshold to avoid binarizing. Most values is either 0 or 1. Fixes to challenge 1. Domain expertise. Consult domain experts to understand the significance of different threshold values in the context of the problem. Exploratory data analysis. Visualize the distribution of the features and identify potential thresholds based on meaningful breakpoints. Grid search. Experiment with a range of threshold values using grid search cross-validation to find the optimal threshold that maximizes model performance. Challenge 2, handling missing values. Sample use case that resulted in challenge 2, missing values in the input data might lead to errors during binarization. Fixes to challenge 2. Imputation. Fill in missing values using strategies like mean, median, or mode imputation before applying the binarizer. Removal. Exclude features with a high percentage of missing values if imputation is not feasible. Separate handling. Develop separate logic for handling missing values within the binarizers. Implementation. sklearn, preprocessing, function transformer. Description. The function transformer class in Sci-Kit is a versatile preprocessing tool that allows you to apply arbitrary functions to your data before feeding it into machine learning models. It essentially acts as a wrapper for your custom function, making it compatible with Sci-Kit's pipeline and other features. Inputs. X, a NumPy array or pandas data frame representing your input data. This is the data that you want to transform using the function you define. Function. A callable function, lambda expression, or any other object that can be called that takes a single argument, the input data X, and returns the transformed data. Outputs. Transformed data. The output of the function transformer is the result of applying your custom function to the input data. The format of the output will depend on the function you define. It can be a NumPy array, pandas data frame, or any other object returned by your function. Steps. Function application. When you apply function transformer to your data, it internally calls your custom function with the input data X. Output. Handling. The function transformer then handles the output of your function, ensuring that the resulting data is in a format that is compatible with Sci-Kit. Metrics. Non-function transformer doesn't directly provide metrics for assessing the transformation. The metrics would depend on the specific function you use. Visualization plots. Non-function transformer does not directly offer visualization plots. However, you can use visualization techniques for the output data after transformation. Fine-tune parameters. Func. This parameter defines the function that you want to apply to your data. It can be any callable object that takes the input data as an argument and returns the transformed data. Validate. This parameter controls how function transformer handles the input data. If set to true default, it will check if the input data has the correct format and raise an error if it doesn't. You can set it to false if you want to bypass this check. Inverse func. This parameter allows you to define an inverse function for your transformation. The inverse function is used to reverse the transformation applied by the function transformer. You can set it to none if you don't want to define an inverse function. Accept sparse. This parameter determines whether the function transformer can accept sparse matrices as input. If set to true, it can handle sparse matrices. Otherwise, it requires dense data. Check inverse. This parameter checks if the inverse function, if defined, is valid. If set to true default, it will verify that the inverse transformation correctly restores the original data. Quarks. This parameter allows you to pass additional keyword arguments to your custom function. Uncertainty methods. Non-function transformer doesn't offer uncertainty quantification methods. Uncertainty would be tied to the function you are using and any related methods it might have. Challenges and fixes. Challenge 1. Function output format is not compatible with downstream models. Sample use case that resulted in challenge 1. You might apply a function that returns a list of lists instead of a NumPy array, which is not directly compatible with many scikit-learn models. Fixes to challenge 1. You can either modify your function to return a NumPy array or use an additional transformer after function transformer to convert the output to the desired format. Challenge 2. Function throws errors or unexpected behavior for specific input data. Sample use case that resulted in challenge 2. The function you are using might encounter edge cases or errors when processing certain types of input data, leading to unexpected results. Fixes to challenge 2. Carefully test your function with different types of data, including edge cases, to ensure it behaves as expected. You might need to modify your function to handle these cases explicitly. Challenge 3. Inverse function doesn't properly reverse the transformation. Sample use case that resulted in challenge 3. You might define an inverse function, but it doesn't correctly restore the original data after applying the transformation. Fixes to challenge 3. Double-check your inverse function logic to ensure it accurately undoes the transformation performed by your original function. You can also use the checkInverse parameter to automatically check for valid inverse functions. sklearn, preprocessing, k-bins discretizer. Description. The k-bins discretizer class in scikit-learn is a transformer that converts continuous numerical features into discrete bins. It allows you to create a specified number of bins for each feature, mapping continuous values within each bin to a single integer. This is useful for preparing data for algorithms that are not suitable for continuous data, e.g. decision trees, reducing the impact of outliers, simplifying data for interpretation. Inputs. X. A NumPy array or pandas data frame containing the data to be discretized. Each column represents a feature. Encode string indicating the encoding scheme to use. Options are 1 hot encodes each bin, creating a binary feature for each bin in a column. Ordinal encodes bins with consecutive integers. Outputs. Transformed XA NumPy array or pandas data frame containing the discretized data. The shape will depend on the encode parameter. Bin edges, a list of arrays. One for each feature. Containing the bin edges. Steps. 1. Binning the data is divided into a specified number of bins for each feature. The bin edges can be determined automatically using different strategies or provided manually. 2. Encoding the continuous values within each bin are encoded based on the chosen encode parameter. Metrics. Bin width measures the size of each bin. Number of bins represents the total number of bins created for each feature. Visualization plots. Histogram. A histogram of the original data can be plotted to visualize the distribution and understand the effectiveness of binning. Heat map. A heat map can be used to visualize the relationship between features after discretization. Fine-tune parameters. NB ins an integer or array like specifying the number of bins for each feature. It can be a single value for equal width bins across features or an array with individual values. For each feature, encode string indicating the encoding scheme. Options are 1 hot or ordinal. Strategy string indicating the strategy for binning. Options are uniform, all bins have equal width. Quantile bins have the same number of samples. K-means bins are determined using the K-means algorithm. Uncertainty methods. Sensitivity analysis varying the number of bins and binning strategy to assess the impact on pay. Results. Challenges and fixes. Challenge 1. Choosing the optimal number of bins. Sample use case. Discretizing a feature with a highly skewed distribution might lead to uneven bin sizes, impacting the results. Fixes. Explore different strategies. Uniform, quantile, K-means and evaluate their performance. Experiment with different bin numbers and visualize the results using histograms to assess pay. Impact on the distribution. Consider using domain knowledge or business understanding to guide the bin selection. Challenge 2. Choosing the right encoding scheme. Sample use case. Choosing one hot encoding when dealing with a high number of bins can lead to high dimensionality and sparse data. Fixes. Use ordinal encoding for smaller numbers of bins. Consider using feature selection or dimensionality reduction techniques to handle high dimensionality if one hot encoding is used. Evaluate the impact of encoding on the performance of the downstream model. Challenge 3. Handling missing values. Sample use case. Missing values in the data can lead to errors or biases in the discretization process. Fixes. Impute missing values before applying K-bins discretizer. Use the missing values parameter to specify how to handle missing values during binning. sklearn, Preprocessing, Kernel Centerer. Description. Kernel Centerer is a class in Sci-Kit sklearn used for centering kernel matrices. It is specifically used in kernel-based machine learning methods, such as kernel ridge regression or support vector machines, to ensure that the kernel matrix has a zero mean. This centering step is crucial for improving the performance of these algorithms. Inputs. XA NumPy array representing the kernel matrix. The kernel matrix is a square matrix where each element represents the similarity between two data points. Outputs. K the centered kernel matrix. X fit the original kernel matrix, but modified in place. This is useful for chained transformations. Steps. Calculate the mean of each row of the kernel matrix. Subtract the mean of each row from the corresponding row of the kernel matrix. Calculate the mean of each column of the kernel matrix. Subtract the mean of each column from the corresponding column of the kernel matrix. Adjust the diagonal elements of the kernel matrix to compensate for the centering operations. Metrics. Non-kernel centerer itself does not directly produce metrics. It is a preprocessing step that prepares data for further analysis. Visualization plots. Non-kernel centerer does not generate visualization plots. Its primary purpose is to transform data for other machine learning algorithms. Fine-tune parameters. Non-kernel centerer does not have any tunable parameters. Uncertainty methods. Non-kernel centerer is deterministic and does not involve any uncertainty estimation. Challenges and fixes. Challenge 1. The input data should be a valid kernel matrix, meaning it should be square and symmetric. Sample use case that resulted in challenge 1 providing a non-square or non-symmetric matrix as input. Fixes to challenge 1 ensure that the input data is a valid kernel matrix before using kernel centerer. Challenge 2. Kernel centerer assumes that the input kernel matrix is already calculated. Sample use case that resulted in challenge 2 trying to use kernel centerer directly on raw data, without first computing the kernel matrix. Fixes to challenge 2 use an appropriate kernel function to compute the kernel matrix from the raw data before applying kernel centerer. sklearn preprocessing label binarizer. Description label binarizer is a transformer in Sci-Kit learn used for encoding categorical features as a one-hot numerical representation. It is particularly useful when working with classification algorithms that require numerical input. Inputs. Input 1. A 1D array of categorical labels. This array represents the raw categorical data that needs to be encoded. Input 2. A list of classes. This optional input specifies the unique classes that should be considered for encoding. If not provided, label binarizer will automatically determine the unique classes from the input data. Outputs. Output 1. A 2D array of binary values. Each row represents a sample, and each column corresponds to a unique class. The value in a cell indicates whether the corresponding sample belongs to the class represented by that column 1 or not 0. Output 2. A list of classes. This list contains the unique classes detected by label binarizer. Steps. Step 1. Class identification. Label binarizer identifies the unique classes present in the input data or from the provided list of classes. Step 2. Binary encoding for each input sample. Label binarizer creates a binary vector where each element corresponds to a class. The element is set to 1 if the sample belongs to that class and 0 otherwise. Metrics. Metric 1. None. Label binarizer is primarily a data preprocessing technique and does not directly evaluate model performance metrics. Metric 2. None. Visualization plots. Visualization plot 1. None. Label binarizer's output is typically used as input for other algorithms and visualization plots are not directly applicable. Visualization plot 2. None. Fine-tune parameters. Parameter 1. Neg label specifies the value to use for negative labels. Default 0. Parameter 2. Post label specifies the value to use for positive labels. Default 1. Uncertainty methods. Uncertainty method 1. None. Label binarizer does not incorporate uncertainty measures as it primarily focuses on deterministic encoding. Uncertainty method 2. None. Challenges and fixes. Challenge 1. Unseen classes. If the input data contains a class not encountered during training, label binarizer will fail to encode it. Sample use case that resulted in challenge 1. A data set containing animal names, where a new animal species is introduced during prediction. Fixes to challenge 1 use a robust encoding technique like one-hot encoding, which can handle new classes gracefully. Challenge 2 data sparsity with a large number of classes. The resulting binary representation can be sparse, potentially affecting the performance of subsequent algorithms. Sample use case that resulted in challenge 2 a dataset with a wide variety of product categories, resulting in a sparse binary representation. Fixes to challenge 2 consider dimensionality reduction techniques like PCA or feature selection to mitigate the effects of sparsity. sklearn preprocessing label encoder. Description: explain in detail. Label encoder is a class in Sci-Kit that transforms categorical features into numerical features. It assigns a unique integer to each category. This is particularly useful for machine learning algorithms that can only work with numerical data. Inputs. Input 1. Explain in detail a 1D array-like object containing categorical data. This can be a list, a NumPy array, or a pandas series. Input 2. Explain in detail none. Outputs. Output 1. Explain in detail a 1D array-like object containing the encoded numerical values corresponding to the original categorical data. Output 2. Explain in detail a dictionary mapping the original categorical labels to their assigned numerical codes. This dictionary is stored in the class's attribute of the label encoder object. Steps. Step 1. Explain in detail. The label encoder first fits itself to the input categorical data. This involves identifying the unique categories present in the data and assigning them unique integer codes. Step 2. Explain in detail. Once fitted, the label encoder can then transform the input data by converting each categorical value into its corresponding numerical code. Metrics. Metric 1. Explain in detail none. Metric 2. Explain in detail none. Visualization plots. Visualization plot 1. Explain in detail none. Visualization plot 2. Explain in detail none. Fine-tune parameters. Parameter 1. Explain in detail none. Parameter 2. Explain in detail none. Uncertainty methods. Uncertainty method 1. Explain in detail none. Uncertainty method 2. Explain in detail none. Challenges and fixes. Challenge 1. Explain in detail data leakage. If the label encoder is fitted on the entire dataset, including both training and test data, it may lead to data leakage. The encoder will learn the mapping between categories and codes based on the test data, potentially introducing information about the test set into the training process. This can result in an overly optimistic evaluation of the model's performance. Sample use case that resulted in challenge 1 using label encoder on the entire dataset before splitting it into training and test sets. Fixes to challenge 1. Fit the label encoder only on the training data, and then use the same fitted encoder to transform both the training and test data. This ensures that the encoder only learns the mapping from the training data, preventing data leakage. Challenge 2. Explain in detail handling new categories. If the label encoder encounters a new category during the transformation process that was not present in the training data, it will raise an error. This can occur, for example, when dealing with real-world data where new categories might emerge over time. Sample use case that resulted in challenge 2 encountering a new category in the test data that was not seen during training. Fixes to challenge 2 to address this. You can either handle new categories by assigning them a new code, for example, by using a placeholder value or by using a different encoding technique, such as one-hot encoder, that can handle unseen categories gracefully. sklearn, preprocessing, multi-label binarizer. Description. The multi-label binarizer is a transformer that converts a collection of multi-label samples into a matrix. Each sample is represented by a binary vector, where each element indicates the presence or absence of a specific label. Inputs. Why this is a list of lists, where each inner list represents the labels associated with a single sample. Outputs. Why bin this is a 2D array of shape n samples. N classes, where each row represents a sample and each column represents a label. Each element is 1 if the label is present in the sample, and 0 otherwise. Steps. The multi-label binarizer first determines the unique labels present in the input data. It then creates a mapping between each label and its corresponding column index in the output matrix. For each sample, the transformer iterates over its labels and sets the corresponding elements in the output matrix to 1. Metrics. Accuracy. This metric measures the proportion of correctly classified samples. Precision. This metric measures the proportion of true positives among the predicted positives. Recall. This metric measures the proportion of true positives among the actual positives. F1 score. This metric is the harmonic mean of precision and recall. Visualization plots. Confusion matrix. This plot shows the distribution of true and predicted labels. Precision recall curve. This plot shows the trade-off between precision and recall for different thresholds. ROC curve. This plot shows the trade-off between true positive rate and false positive rate for different thresholds. Fine-tune parameters. Classes. This parameter specifies the list of classes to consider. If not provided, the classes are automatically determined from the input data. Uncertainty methods. Confidence scores. Each predicted label can be associated with a confidence score, indicating the certainty of the prediction. Challenges and fixes. Challenge 1. The multi-label binarizer can be inefficient for large datasets with a large number of labels, as it requires creating a matrix with a number of columns equal to the number of labels. Sample use case that resulted in challenge 1. A dataset with millions of samples and thousands of unique labels. Fixes to challenge 1. Consider using a sparse representation for the output matrix, as this can significantly reduce memory usage. Challenge 2. The multi-label binarizer can produce a very sparse output matrix, which can be inefficient for certain algorithms. Sample use case that resulted in challenge 2. A dataset with a high proportion of samples with a small number of labels. Fixes to challenge 2. Consider using a different encoding scheme that produces a less sparse representation, such as a one-hot encoding. sklearn preprocessing max abs scaler. Description. Max abs scaler scales features by dividing each value by the maximum absolute value in each feature. This results in a range of -1 for all features, making the data suitable for algorithms that are sensitive to feature scaling. Inputs. X. A numerical array or pandas data frame containing the data to be scaled. Outputs. X. Scaled. A transformed version of X with each feature scaled by the maximum absolute value in that feature. Steps. Calculate the maximum absolute value for each feature in the input data. Divide each value in the input data by the corresponding maximum absolute value, effectively scaling the data to the range -1. 1. Metrics. No specific metrics are associated with max abs scaler as it only performs scaling and does not directly impact model performance. However, the scaled data may influence the performance of subsequent algorithms. Visualization plots. Box plots. A box plot visualization can be used to compare the distribution of features before in After scaling. Highlighting the impact of the transformation. Scatterplots. Scatterplots can be used to visually assess the relationships between features before and after scaling, helping identify potential changes in correlation patterns. Fine-tune parameters. Copy true by default. If true, a copy of X will be created. If false, X will be overwritten. Uncertainty methods. No specific uncertainty methods are associated with max_abs scalar as it is a deterministic transformation. Challenges and fixes. Challenge 1. Zero values in the input data. Sample use case that resulted in challenge 1. If a feature has a maximum absolute value of 0, dividing by it would result in an error. Fixes to challenge 1. Ensure that the data contains at least one non-zero value in each feature. Consider using other scaling methods like min-max scalar or robust scalar if zero values are prevalent. Challenge 2. Outlier values. Sample use case that resulted in challenge 2. Outlier values can significantly influence the maximum absolute value, leading to a compressed scaling for most values. Fixes to challenge 2. Remove or handle outliers before applying max_abs scalar. Consider using alternative scaling methods like robust scalar, which is less sensitive to outliers. sklearn preprocessing min-max scalar. Description. Explain in detail. Min-max scalar is a data preprocessing technique in scikit-learn. sklearn that transforms features to a specified range, typically between 0 and 1. It does this by subtracting the minimum value of the feature and dividing by the range maximum value minus minimum value. This scaling method is useful for algorithms that are sensitive to feature scales, such as k-nearest neighbors, support vector machines, and neural networks. Inputs. Input 1. Explain in detail. The input to min-max scalar is a NumPy array or pandas data frame containing the features to be scaled. The features can be of any numerical data type, such as integers or floating point numbers. Input 2. Explain in detail. The min-max scalar also takes a few optional parameters, such as feature range. This parameter specifies the desired range for the transformed features. The default value is 0, 1, but it can be customized. Copy. This parameter indicates whether to create a copy of the input array or to modify the array. In place, the default value is true, which creates a copy. Outputs. Output 1. Explain in detail. The output of min-max scalar is a NumPy array or pandas data frame with the same shape as the input, but with the features scaled to the specified range. Output 2. Explain in detail. In addition to the scaled data, the min-max scalar object also stores the minimum and maximum values of the original features, which can be used to reverse the scaling later. Steps. Step 1. Explain in detail. The min-max scalar first calculates the minimum and maximum values of each feature in the input data. Step 2. Explain in detail. Then, for each feature, it subtracts the minimum value from each data point and divides the result by the range maximum minus minimum. This transforms the data to a range between 0 and 1. Metrics. Metric 1. Explain in detail. There are no specific metrics directly associated with the min-max scalar itself. However, the effectiveness of min-max scalar is evaluated indirectly through the performance of the machine learning model that uses the scaled data. Metric 2. Explain in detail. For example, if the machine learning model achieves higher accuracy or lower error with the scaled data than with the original data, it indicates that min-max scalar has been beneficial. Visualization plots. Visualization plot 1. Explain in detail. Box plots or histograms can be used to visualize the Distribution of features before and after scaling with min-max scaler. This can help assess the impact of the scaling on the data. Visualization plot to explain in detail. Scatter plots can be used to compare the relationships between pairs of features before and after scaling. This can help visualize how scaling might have affected the correlations between features. Fine-tune parameters. Parameter 1. Explain in detail feature range. Adjusting the feature range parameter allows for customization of the output scale. For example, setting it to -1. One would scale the features to the range of -1 to 1. Parameter 2. Explain in detail copy. Setting copy to false can reduce memory usage and improve performance, especially when working with large datasets. However, it modifies the input array in place, which may not be desirable in some cases. Uncertainty methods. Uncertainty method 1. Explain in detail. There are no specific uncertainty methods directly associated with min-max scaler itself. The uncertainty in the scaled data is inherited from the uncertainty in the original data. Uncertainty method 2. Explain in detail to assess uncertainty in the scaled data. Methods such as confidence intervals or error bars could be applied to the original data before scaling. Challenges and fixes. Challenge 1. Explain in detail outliers. Min-max scaler is sensitive to outliers. If a dataset contains extreme values, they can disproportionately influence the scaling process, leading to compressed ranges for other data points. Sample use case that resulted in challenge 1. A dataset of house prices with one outlier representing a mansion worth millions of dollars could cause the other houses to be compressed into a very small range. Fixes to challenge 1. Consider using robust scaling methods like robust scaler or standard scaler, which are less affected by outliers. Alternatively, handle outliers before scaling using techniques like capping or removal. Challenge 2. Explain in detail data with large ranges. If the features in a dataset have significantly different ranges, min-max scaler may not be the most effective scaling method. It can lead to features with smaller ranges dominating the scaling process. Sample use case that resulted in challenge 2. A dataset containing features like age range 0 to 100 and income range 100 might be better suited for standard scaler, which standardizes the features to have zero mean and unit variance. Fixes to challenge 2. Consider using other scaling methods like standard scaler or robust scaler, which handle features with varying ranges more effectively. Alternatively, pre-process the features by applying logarithmic transformations or other techniques to reduce the range differences. sklearn preprocessing normalizer. Description. The normalizer is a preprocessing technique used to rescale the features of a dataset so that each sample row has a unit norm. This means the sum of squares of all features in each sample will be equal to 1. It is primarily used to ensure that features with larger magnitudes don't dominate the analysis, especially in algorithms that are sensitive to feature scaling. Inputs. X. A NumPy array or pandas data frame containing the data. Each row represents a sample, and each column represents a feature. Outputs. X. Normalized. A NumPy array or pandas data frame containing the normalized data. Each sample has a unit norm. Steps. Reshaping. If the input data is not a 2D array, e.g., it's a 1D array, the normalizer will reshape it into a 2D array with each sample as a row. Norm calculation for each sample row in the dataset. The norm, usually Euclidean norm, is calculated. Scaling. Each feature in the sample is divided by the calculated norm, resulting in the normalized sample. Metrics. L1 norm the sum of the absolute values of all features in a sample. L2 norm the square root of the sum of squares of all features in a sample. Max norm the maximum absolute value of all features in a sample. Visualization plots. Scatter plot comparing the original data points with the normalized data points in a scatter plot. Can visually demonstrate the effect of normalization. Fine-tune parameters. Norm a string specifying the norm to use. Options include L1, L2, max, defaults to L2 Euclidean norm. Uncertainty methods. None the normalizer itself doesn't incorporate any uncertainty methods. Challenges and fixes. Challenge 1 data skewness if the original data has significant skewness. Normalization might not be the best choice, as it can amplify the effect of outliers. Sample use case that resulted in challenge 1. Imagine a dataset with features representing salaries. A few individuals with extremely high salaries might disproportionately affect the normalization process, leading to inaccurate results for most other individuals. Fixes to challenge 1. Consider using robust scaling methods like robust scaler or quantile transformer, which are less sensitive to outliers. Challenge 2. Interpretability after normalization. The original magnitudes of features are lost. This can make it harder to interpret the results, especially if domain knowledge is important. Sample use case that resulted in challenge 2 in a medical dataset. Normalization might make it difficult to determine the relative importance of different features, as the normalized values no longer reflect the original scales. Fixes to challenge 2. Document the normalization process and the specific norm used. Consider using methods like standardization standard scaler that preserve the relative scales of features while centering and scaling the data. sklearn preprocessing 1 hot encoder. Description. Explain in detail. 1 hot encoder is a preprocessing technique used in machine learning to convert categorical features into a numerical representation suitable for machine learning algorithms. It achieves this by creating a binary vector for each category, where a single element is set to 1 representing the presence of that category and all other elements are set to 0. Inputs. Input 1. Explain in detail input data, typically in the form of a NumPy array or pandas data frame, where categorical features are represented as strings or integers. Input 2. Explain in detail handle unknown. Ignore default to handle unseen categories during testing, or error to raise an error. Outputs. Output 1. Explain in detail transformed data with 1 hot encoded features, resulting in a sparse matrix or a dense array. Output 2. Explain in detail the mapping between categories and their corresponding encoded columns, which can be useful for interpreting the encoded features. Steps. Step 1. Explain in detail identifies unique categories within the input categorical features. Step 2. Explain in detail creates a binary vector for each category, where a single element is set to 1 and all other elements are set to 0. This vector represents the presence or absence of that specific category. Metrics. Metric 1. Explain in detail. No specific metrics are used to evaluate the performance of 1 hot encoder itself, as it is a preprocessing technique. However, the effectiveness of the encoded features can be assessed by the performance of the subsequent machine learning model using the encoded data. Metric 2. Explain in detail metrics such as accuracy, precision, recall, F1 score, and AUC can be used to evaluate the performance of the machine learning model that uses the encoded features. Visualization plots. Visualization plot 1. Explain in detail. A heat map can be used to visualize the one-hot encoded features, showcasing the presence or absence of categories across different instances. Visualization plot 2. Explain in detail. A bar chart can be used to visualize the distribution of categories within the input data. Fine-tune parameters. Parameter 1. Explain in detail. Categories specifies the unique categories for each feature. If not provided, it will automatically infer them from the input data. This parameter allows for manual control over the encoding scheme, especially useful when dealing with known categories or handling unseen categories during testing. Parameter 2. Explain in detail. Sparse determines whether to return the output as a sparse matrix, true, default, or a dense array, false. Sparse matrices are more memory efficient when dealing with high-dimensional data with many zeros. Uncertainty methods. Uncertainty method 1. Explain in detail. One-hot encoder itself does not directly incorporate uncertainty methods. However, uncertainty in the encoded features can be addressed by using techniques like Bayesian inference in the subsequent machine learning model that uses the encoded data. Uncertainty method 2. Explain in detail. Ensemble methods, such as bagging or boosting, can be used with the machine learning model to estimate uncertainty in the predictions. Challenges and fixes. Challenge 1. Explain in detail. High dimensionality one-hot encoding can significantly increase the dimensionality of the data, especially when dealing with categorical features with a large number of unique categories. This can lead to the curse of dimensionality, making it challenging for some machine learning models to learn effectively. Sample use case that resulted in challenge 1. A dataset with a categorical feature representing product categories with hundreds of unique categories, resulting in a large number of one-hot encoded columns. Fixes to challenge 1. Feature selection techniques like feature importance analysis can be used to identify and remove redundant or less informative one-hot encoded columns. Dimensionality reduction techniques like principal component analysis (PCA) or TSNE can be applied to reduce the dimensionality of the encoded data. Challenge 2. Explain in detail handling unseen categories during testing or when encountering new data with previously unseen categories. One-hot encoder may raise an error by default or encode them with zeros if handle unknown is set to ignore. Sample use case that resulted in challenge 2. A dataset with product categories, where a new product category appears during testing that was not present during training. Fixes to challenge 2. Set handle unknown. Ignore. This will ignore unseen categories during testing, effectively treating them as absent. Preprocess the data during training. Ensure the input data covers all possible categories to avoid encountering unseen categories during testing. Using handle in non-error. This option will raise an error when encountering unseen categories, forcing you to handle them explicitly. You can either add the new categories to the training data or remove the corresponding instances with the unseen categories. sklearn, preprocessing, ordinal encoder. Description. The ordinal encoder transforms categorical features into numerical features by assigning a unique integer to each category. It is a simple and commonly used preprocessing step for machine learning models that require numerical inputs. Inputs. X a 2D array-like object, where each row represents a data sample and each column represents a feature. The input data should contain categorical features that need to be encoded. Categories. A list of categories for each feature. where each list item corresponds to a column in the input data. If not provided, the encoder will infer categories from the input data. Outputs. Transformed data: a 2D array-like object containing the encoded numerical values. The transformed data will have the same shape as the input data, but the categorical features will be replaced with their corresponding integer representations. Categories: an array containing the categories learned during fitting. Steps. Fit: the encoder learns the unique categories present in the input data. If categories are provided, the encoder uses those instead of inferring them from the data. Transform: the encoder assigns integer values to each category based on the order they were encountered during fitting. Metrics: none. Visualization plots: none. Fine-tune parameters. Handle unknown determines how the encoder handles unknown categories during transformation. Use encoded value assigns the maximum integer value 1 to unknown categories, while error raises an error. D-type: the data type of the encoded output. Uncertainty methods: none. Challenges and fixes. Challenge 1: the order in which categories are encountered during fitting affects the integer assigned to each category. Sample use case: if the encoder is trained on a dataset where blue is encountered before red, then blue will be assigned the integer 0 and red will be assigned 1. If a new dataset with a different order of categories is used for transformation, red may be assigned 0 and blue 1, leading to unexpected results. Fixes. Ensure that the order of categories in the training and test datasets is consistent. Consider using a more sophisticated encoding scheme, such as one-hot encoding, that is less sensitive to the order of categories. Challenge 2: the encoder cannot handle unknown categories during transformation if handle unknown is set to error. Sample use case: if a new category green is encountered during transformation, the encoder will raise an error. Fixes. Set handle unknown to use encoded value to allow the encoder to handle unknown categories. Ensure that the data used for transformation contains only categories encountered during fitting. Challenge 3: the encoder does not handle missing values. Sample use case: if a data sample contains a missing value in a categorical feature, the encoder will raise an error. Fixes. Impute missing values before using the encoder. Consider using a different encoding scheme, such as one-hot encoding, that can handle missing values more gracefully. sklearn, preprocessing, polynomial features. Description. The polynomial features class in Sci-Kit Learn sklearn is a powerful tool for transforming your data. By creating polynomial features, it's commonly used in machine learning to improve the flexibility of your models, especially when dealing with nonlinear relationships between input variables and the target variable. Inputs. X, a 2D array of numerical input features. This array represents your data, where each row corresponds to a data point and each column represents a feature. Degree: the degree of the polynomial features to generate. For example, degree 2 will create quadratic features x12, x22, x1 by 2, etc. Outputs. Xpoly: a transformed array of polynomial features. Each column in Xpoly corresponds to a unique polynomial combination of the original features. N output features: an integer indicating the total number of polynomial features created. Steps. Feature generation: the algorithm generates all possible combinations of input features up to a specified degree. These combinations include the original features themselves degree 1, squared terms degree 2, interaction terms products of different features, and so on. Feature matrix transformation. It creates a new matrix exponentially where each column represents one of the newly generated polynomial features. Metrics. Model performance. Polynomial features often lead to improved model performance, especially when dealing with nonlinear relationships in the data. However, it's crucial to use techniques like regularization to prevent overfitting. Feature interpretability. The interpretation of polynomial features can be more complex compared to the original features, as they represent interactions and nonlinear relationships. Visualization plots. Scatter plots to visualize the nonlinear relationships in your data. You can create scatter plots of the target variable against each of the original features. Heat maps. Heat maps can be helpful to visualize the interactions between features and the target variable. Fine-tune parameters. Degree. This parameter controls the complexity of the polynomial features. Higher degrees can lead to more complex models but might overfit the data. Start with low degrees 2 or 3 and gradually increase if necessary. Interaction only. This parameter determines whether to include only interaction terms products of different features or all possible combinations of features. Setting it to true can simplify the model and reduce the number of features. Uncertainty methods. Cross-validation. Use techniques like cross-validation to evaluate your model's performance on unseen data and estimate the uncertainty in your predictions. Bootstrapping. Bootstrapping can be used to assess the variability of your model's predictions and estimate confidence intervals. Challenges and fixes. Challenge 1. Overfitting. Using high-degree polynomials can lead to overfitting, where the model performs very well on the training data but poorly on new, unseen data. Sample use case that resulted in challenge 1. A model using a high-degree polynomial feature with a limited dataset may fit the training data perfectly but generalize poorly to new data points. Fixes to challenge 1. Regularization. Techniques like L1 and L2 regularization can help prevent overfitting by penalizing complex models. Cross-validation. Use cross-validation to evaluate the model's performance on unseen data and choose the degree that balances performance and generalization ability. Feature selection. Select relevant features using techniques like feature importance or feature selection algorithms. Challenge 2. Curse of dimensionality. As the degree of the polynomial features increases, the number of features grows rapidly, leading to the curse of dimensionality. This can make the model computationally expensive and prone to overfitting. Sample use case that resulted in challenge 2. When dealing with a large number of features and using a high-degree polynomial, the number of features can explode, making the training process slow and potentially causing overfitting. Fixes to challenge 2. Feature selection. Apply feature selection techniques to reduce the number of features. Dimensionality reduction. Use dimensionality reduction techniques like PCA principal component analysis to reduce the dimensionality of the data. Lower degree. Use a lower degree polynomial to decrease the number of features. sklearn preprocessing power transformer. Description. The power transformer class in Sci-Kit Learn sklearn is a data preprocessing technique used to transform features with skewed distributions to more closely resemble a normal distribution. This is achieved by applying a power transformation, such as the Yo-Johnson or Box-Cox transformation, to the input features. Transforming skewed data can be beneficial for various machine learning algorithms that assume normally distributed data, leading to better performance and more accurate results. Inputs. X a two-dimensional array of numerical features. Method. The type of power transformation to apply. Options include: Yo-Johnson applies the Yo-Johnson transformation, which handles both positive and negative values. Box-Cox applies the Box-Cox transformation, which requires strictly positive values. Outputs. X transformed a two-dimensional array containing the transformed features. Lambda, the estimated optimal power parameter for the transformation. Steps. Feature scaling. The power transformer initially scales the features to have a mean of 0 and a standard deviation of 1. Power transformation. It applies the chosen transformation Yo-Johnson or Box-Cox to the scaled features, adjusting their distribution to be closer to normal. Metrics. Skewness. The skewness of the transformed data is reduced, indicating a more symmetrical distribution. Kurtosis. The kurtosis of the transformed data can become closer to 3, suggesting a distribution closer to normality. Visualization plots. Histograms. Visualizing the distributions of the original and transformed features using histograms helps understand the effect of the transformation. QQ plots. Quantile plots. QQ plots compare the quantiles of the transformed data to a normal distribution, providing a visual assessment of the normality assumption. Fine-tune parameters. Method. The choice of transformation method Yo-Johnson or Box-Cox can influence the results, depending on the data characteristics. Standardize. A Boolean flag indicating whether to standardize the data before applying the transformation. True by default. Uncertainty methods. Bootstrapping. Performing multiple transformations with resampled data can estimate the uncertainty in the estimated lambda parameter. Challenges and fixes. Challenge 1. Data with 0 or negative values. Sample use case. When using the Box-Cox transformation, features with 0 or negative values will result in errors. Fixes. Apply the Yo-Johnson transformation. This method can handle both positive and negative values. Add a small constant. Adding a small constant to the features can shift them slightly above 0, allowing the Box-Cox transformation to be used. Challenge 2. Limited effectiveness for highly non-normal distributions. Sample use case. If the data has extreme outliers or a highly non-normal distribution, the power transformer might not be able to fully achieve normality. Fixes. Consider alternative transformations. Other transformations like the log transformation or the Box-Cox transformation with a more flexible power parameter might be more suitable. Explore outlier handling. Removing or handling outliers appropriately can improve the effectiveness of the power transformer. Sklearn. Preprocessing. Quantile transformer. Description. The quantile transformer is a feature transformation technique that maps the features to a uniform or Gaussian distribution. It essentially converts the original distribution of each feature to a new distribution, which is either uniform or Gaussian, regardless of the original distribution. It achieves this by mapping the percentiles of the original data to the percentiles of the target distribution. Inputs. X. This is the input data, represented as a two-dimensional array matrix where each row corresponds to a sample and each column represents a feature. Output distribution. This parameter specifies the target distribution for the transformed features. It can be set to uniform for a uniform distribution or normal for a Gaussian distribution. Outputs. Transformed X. The transformed feature matrix, where each feature has the specified output distribution. Steps. Calculate the quantiles for the input data. The quantile transformer first computes the quantiles for each feature in the input data. Map quantiles to target distribution. The calculated quantiles are then mapped to the quantiles of The target distribution, either uniform or Gaussian, transform the input data based on the mapped quantiles. The original data points are transformed to the desired distribution. Metrics. Quantile scores. The quantile scores after the transformation can be used to assess how well the desired distribution is achieved. Distribution plots visualizing the distributions of the features before and after the transformation can provide insights into the effectiveness of the quantile transformer. Visualization plots. Histogram plots comparing the histograms of the features before and after transformation can illustrate the change in distribution. Probability density plots plotting the probability density functions of the features before and after transformation can further highlight the transformation's impact. Fine-tune parameters. Output distribution uniform, default or normal. This determines the target distribution for the transformed features. N quantiles. This parameter specifies the number of quantiles to use when computing the quantile transformation. A higher value of n quantiles results in a more precise transformation, but might lead to longer computation time. Random state. This parameter allows you to control the randomness in the transformation, which can be useful for reproducibility. Uncertainty methods. Bootstrapping. This method involves resampling the data with replacement and performing a quantile transformer on each bootstrap sample. The resulting transformed features can then be used to estimate the uncertainty in a transformation. Challenges and fixes. Challenge 1. Handling outliers. Outliers can have a significant impact on the quantile transformation, potentially distorting the target distribution. Sample use case that resulted in challenge 1 when dealing with a data set containing a few extreme values. The quantile transformation might shift the majority of the data towards the extremes, resulting in a distorted distribution. Fixes to challenge 1. Preprocessing. Implement outlier detection and removal techniques before applying a quantile transformer. Capping. Limit the extreme values to a certain range to reduce their influence. Robust quantile estimation. Use robust quantile estimation techniques that are less sensitive to outliers. Challenge 2. Memory consumption. The quantile transformer can require significant memory, especially when dealing with large datasets. Sample use case that resulted in challenge 2 when working with a dataset with millions of samples and thousands of features. The memory required to store the quantiles and perform the transformation might become excessive. Fixes to challenge 2. Chunking. Process the data in smaller chunks to reduce memory usage. Sparse data representation. If the data is sparse, consider using sparse data structures to reduce memory consumption. Memory optimization. Implement memory optimization techniques to reduce the memory footprint of the algorithm. sklearn. Preprocessing. Robust scaler. Description. Robust scaler transforms features by removing the median and scaling the data according to the quantile range. This method is less prone to outliers in the data than the standard scaler. Inputs. X. A numerical array containing the features to be scaled. This can be a NumPy array, pandas data frame, or a similar structure. Outputs. X. Scaled. A transformed array containing the scaled features. The data is centered around 0 and scaled to a specified range. Steps. Calculate the median of each feature. Calculate the interquartile range IQR of each feature. The IQR is the difference between the 75th percentile and the 25th percentile. Center the data by subtracting the median from each feature. Scale the data by dividing by the IQR. Metrics. IQR interquartile range. Median. The central value of a sorted dataset. Visualization plots. Box plots visualize the distribution of the data before and after scaling. To assess the impact of the transformation, scatter plots plot the features against each other to check for any potential distortions introduced by the scaling. Fine-tune parameters. With centering Boolean. Default true. If true, center the data before scaling. If false, do not center the data. Quantile range tuple of floats. Default 25.0. 75.0. The quantile range used to calculate the scaling factor. The data is scaled such that the quantile range is equal to 1. Uncertainty methods. Bootstrapping resample the data with replacement to estimate the variability of the scaling. Parameters. Confidence intervals. Construct confidence intervals around the scaling parameters to quantify K. Uncertainty. Challenges and fixes. Challenge 1. The robust scaler can be sensitive to extreme outliers that lie outside the IQR. Sample use case that resulted in challenge 1. A dataset with a few extremely large values might cause the robust scaler to scale the data in a way that emphasizes these outliers. Fixes to challenge 1. Consider removing extreme outliers before scaling the data. Use a different scaling method, like the standard scaler, if the data has a Gaussian distribution. Challenge 2. The robust scaler can be less effective when the data has a skewed distribution. Sample use case that resulted in challenge 2. A dataset with a long tail on one side of P. Distribution might not be well scaled by the robust scaler. Fixes to challenge 2. Consider applying a transformation to the data to make it more symmetric before scaling. Use a different scaling method, like the standard scaler, if the data has a Gaussian distribution. sklearn preprocessing spline transformer. Description: the spline transformer from Sci-Kit Learn is a preprocessing technique that allows you to transform numerical features in your dataset using spline functions. Splines are piecewise polynomial functions that can approximate complex relationships between input features and the target variable. This transformation can be particularly beneficial when your data exhibits nonlinear patterns that linear models might struggle to capture. Inputs. Input 1 array like of shape n samples. N features. This input represents your dataset where each row corresponds to a data point and each column represents a feature. The transformer will operate on numerical features within this dataset. Input 2 the feature index or indices where you want to apply the spline transformation. If not specified, the transformer will be applied to all numerical features. Outputs. Output 1 transformed array like of shape n samples. N output features. This output represents the transformed data. The number of output features depends on the degree of the spline and the number of knots specified. For example, a cubic spline with 5 knots would produce 8 new features degree knots. Output 2 nd array of shape n output features. A list of feature names for the transformed features. It is a useful output when you want to track the transformed features in downstream analysis. Steps. Step 1 feature selection. The transformer identifies the features to which the spline transformation will be applied based on the specified feature indices. Step 2 spline transformation. The selected features are transformed using the specified spline function, e.g., cubic spline, B-spline. The degree of the spline and the number of knots determine the complexity of the transformation and the number of new features generated. Metrics. Metric 1 R² are a common metric used to evaluate the goodness of fit of the model after a spline transformation. Higher R² values indicate a better fit of the model to the data. Metric 2 mean squared error MSE measures the average squared difference between the predicted and Actual values. Lower MSE values indicate better model performance. Visualization plots. Visualization plot 1 scatter plots visualize the relationship between the original feature and pay. Target variable before and after the spline transformation to see how the transformation captures the nonlinear patterns. Visualization plot 2 partial dependence plots illustrate the relationship between a transformed feature and the target variable, helping to understand the impact of the transformation on the model's predictions. Fine-tune parameters. Parameter 1 degree. This parameter determines the degree of the spline polynomial. Higher degrees lead to more complex curves, but also risk overfitting if not carefully chosen. Parameter 2 n knots. The number of knots controls the smoothness of the spline. More knots allow the spline to fit the data more closely, but can lead to overfitting if excessive. Uncertainty methods. Uncertainty method 1 bootstrap resampling. Generate multiple datasets by sampling with replacement from the original dataset. Apply the spline transformation to each bootstrapped dataset and measure the variation in pay. Transformed features to estimate uncertainty. Uncertainty method 2 Bayesian methods use Bayesian techniques to incorporate prior beliefs about the parameters of the spline function. The posterior distribution of the parameters provides an indication of uncertainty. Challenges and fixes. Challenge 1 Overfitting. Choosing too many knots or a high degree of the spline can lead to overfitting, where the spline model fits the training data too closely and performs poorly on unseen data. Sample use case that resulted in challenge 1 A dataset with a small number of data points where a high-degree spline with many knots is used, leading to a model that captures noise in the training data but generalizes poorly. Fixes to challenge 1. Regularization techniques. Use techniques like L1 or L2 regularization to penalize complex models and prevent overfitting. Cross-validation. Divide the dataset into training and validation sets. Use the training set to fit the model and the validation set to assess its performance. Adjust the parameters of the spline degree and knots to achieve the best performance on pay. Validation set. Challenge 2 Computational complexity. Increasing the degree or the number of knots can significantly increase the computational complexity of the spline transformation. Sample use case that resulted in challenge 2 dealing with a dataset with millions of data points and a high degree spline with many knots, leading to long processing times. Fixes to challenge 2. Dimensionality reduction. Apply dimensionality reduction techniques before the spline transformation to reduce the number of features and simplify the model. Efficient algorithms utilize algorithms specifically designed for spline fitting, such as B-spline algorithms, which are optimized for computational efficiency. Parallel processing. Exploit parallel processing capabilities to distribute the computational load across multiple cores or machines, reducing overall processing time. sklearn preprocessing target encoder. Description. Target encoder is a feature engineering technique used to encode categorical features by replacing each category with the mean or other statistic of the target variable for that category. It helps to improve the performance of machine learning models by converting categorical data into a numerical format that models can understand. Inputs. X. A pandas data frame or array containing the categorical features to be encoded. Y. A pandas series or array containing the target variable. Outputs. Zencoded. A pandas data frame or array containing the encoded categorical features. Target mean. A dictionary mapping each category to its corresponding mean target value. Steps. Calculate the mean target value for each category in the categorical feature. Replace each category in the input data with its corresponding mean target value. Metrics. Accuracy measures the percentage of correctly predicted instances. Precision measures the proportion of correctly predicted positive instances among all instances predicted as positive. Recall measures the proportion of correctly predicted positive instances among all actual positive instances. F1 score the harmonic mean of precision and recall. Visualization plots. Feature importance plot visualizes the importance of each encoded feature in predicting a target variable. Confusion matrix shows the distribution of correctly and incorrectly classified instances. Fine-tune parameters. Smoothing. A smoothing parameter that controls the influence of the global mean on the category mean. Uncertainty methods. Confidence intervals. Calculate confidence intervals for the category means to quantify a uncertainty in the encoding. Challenges and fixes. Challenge 1. Overfitting. The encoder can overfit to the training data if there are too few instances for some categories. Sample use case that resulted in challenge 1. A dataset with a small number of instances for a certain category may result in an overfitted encoding for that category. Fixes to challenge 1. Use a smoothing parameter to regularize the category means. Use a larger dataset to reduce the impact of small sample sizes. Challenge 2. Data leakage. The encoder can introduce data leakage if the target variable is used to encode the features during training. Sample use case that resulted in challenge 2. If the target variable is used to encode the features during cross-validation, the model may learn from the target variable, leading to an unrealistic performance estimate. Fixes to challenge 2. Use a different encoding method, such as one-hot encoding, for features that are likely to cause leakage. Train the model separately on the training and validation sets to prevent leakage. sklearn, preprocessing, add dummy feature. Description. The add dummy feature function in Sci-Kit Learn's preprocessing module is a simple utility that adds a column of ones to a given array or sparse matrix. This is often used in machine learning to ensure that a linear model has an intercept term. Inputs. X. A numpy array or sparse matrix of shape n samples. N features. Value. A constant value to add as the dummy feature. Default is 1.0. Outputs. X out. A numpy array or sparse matrix of shape n samples. N features 1. Steps. It checks if the input is a sparse matrix or a numpy array. If it is a sparse matrix, it converts it to a dense numpy array. It creates a column of ones with the same number of rows as the input. It horizontally stacks the input array in the column of ones, adding the dummy feature to the existing data. Metrics. This function is not used for any specific metrics. It primarily serves as a preprocessing step for linear models. Visualization plots. This function does not produce any visualization plots. Fine-tune parameters. Value. This parameter allows you to specify the constant value used for the dummy feature. The default value is 1.0, but you can adjust it based on your specific requirements. Uncertainty methods. This function does not handle uncertainty. Challenges and fixes. Challenge 1 none. Challenge 2 none. sklearn, preprocessing, binarize. Description. Binarize data set feature values to 0 or 1 according to a threshold. Inputs. X array like sparse matrix or pandas data frame. Data to binarize. where n samples is the number of samples and n features is the number of features. Threshold float. Default 0.0. Feature values below or equal to this threshold are replaced by 0. Above it by 1. Outputs. X binarized ND array or sparse matrix. Shape n samples. N features. Binarized input data. Steps. Iterate over each feature in the input data. Compare each feature value with the given threshold. Replace values below or equal to the threshold with 0 and values above it with 1. Metrics. Accuracy. It measures the percentage of correctly classified instances, providing a general sense of model performance in terms of how well it predicts the target variable. Precision. It indicates the proportion of correctly predicted positive instances among all instances predicted as positive, highlighting the model's ability to avoid false positives. Recall. It measures the proportion of correctly predicted positive instances among all actual positive instances, reflecting the model's ability to capture all positive cases. Visualization plots. Feature distribution plot. This plot displays the distribution of values for each feature after binarization. It can help visualize the impact of binarization on the data. Confusion matrix. A confusion matrix visualizes the classification performance by showing the number of true positives, true negatives, false positives, and false negatives. Fine-tune parameters. Threshold. This parameter controls the cutoff point for binarizing the data. Adjusting this threshold can influence the outcome of the binarization process. Uncertainty methods. Confidence intervals. These intervals represent the range of values within which the true population parameter is likely to lie with a certain degree of confidence. Challenges and fixes. Challenge 1. Choosing an optimal threshold for binarization. Sample use case that resulted in challenge 1 when data has a wide range of values. Selecting an appropriate threshold for binarization becomes crucial to ensure meaningful transformation. Fixes to challenge 1. Use domain knowledge to guide threshold selection. Experiment with different thresholds and evaluate model performance to determine the best value. Challenge 2. Handling missing values. Sample use case that resulted in challenge 2 missing values can hinder binarization, as the algorithm needs to compare values against the threshold. Fixes to challenge 2. Impute missing values using appropriate techniques like mean, median, or mode imputation before applying binarization. Consider using specialized binarization methods that handle missing values directly. sklearn, preprocessing, label binarize. Description. The label binarize function in scikit-learn is used to transform categorical labels into a binary matrix representation. This is particularly useful for multi-class classification problems where you want to represent each class as a separate binary column. Inputs. Why the input array of labels? It can be a 1D array or a 2D array where each row represents a sample's label. The labels should be integers or strings representing the categories. Classes. An optional list or array specifying the unique classes in the dataset. If not provided, the unique values in Y will be used. Outputs. Y. A binary matrix where each row represents a sample and each column represents a class. The value in each cell indicates whether the corresponding sample belongs to the corresponding class 1 or not. 0. Classes. A list of the unique classes in the dataset. Steps. The function first identifies the unique classes present in the input labels. It then creates a binary matrix with one column per unique class. For each sample in the input labels, the function sets the corresponding column in the binary matrix to 1 if the sample belongs to that class and 0 otherwise. Metrics. Accuracy. This metric measures the percentage of correctly classified samples. Precision. This metric measures the proportion of correctly classified positive samples among all samples predicted as positive. Recall. This metric measures the proportion of correctly classified positive samples among all actual positive samples. F1 score. This metric combines precision and recall into a single score. Visualization plots. Confusion matrix. This plot visualizes the performance of the classification model by showing the number of true positives, true negatives, false positives, and false negatives. ROC curve. This plot shows the trade-off between true positive rate and false positive rate for different classification thresholds. Fine-tune parameters. Classes. This parameter allows you to specify the desired order of the classes in the output. Binary matrix. Uncertainty methods. Confidence score. This method assigns a confidence score to each prediction based on the distance from the decision boundary. Challenges and fixes. Challenge 1. Incorrectly handling labels with multiple classes. Sample use case that resulted in challenge 1. If a sample has multiple labels and the class's parameter is not explicitly specified, the function may incorrectly interpret the labels. Fixes to challenge 1. Specify the class's parameter explicitly to ensure the correct handling of multi-class labels. Challenge 2. Inconsistent label encoding between training and testing data. Sample use case that resulted in challenge 2. If the labels in the training data and testing data are encoded differently, the model may not be able to generalize well. Fixes to challenge 2. Ensure that the labels are encoded consistently across the training and testing datasets using a consistent label encoder. sklearn preprocessing max abs scale. Description. The max abs scaler scales each feature by dividing by the maximum absolute value of that feature. This results in a data set where all features have values between -1 and 1. Inputs. A 2D NumPy array representing the data with features as columns. Outputs. Scaled A 2D NumPy array representing the scaled data with features as columns. Steps. For each feature in X, calculate the maximum absolute value. Divide each feature in X by its respective maximum absolute value. Metrics. No specific metrics are associated with max abs scaler. Visualization plots. Scatter plots can be used to visualize the distribution of data before and after scaling. Box plots can be used to visualize the distribution of each feature before and after scaling. Fine-tune parameters. None. Uncertainty methods. No uncertainty methods are associated with max abs scaler. Challenges and fixes. Challenge 1. The max abs scaler can be sensitive to outliers in the data. Sample use case that resulted in challenge 1. If a feature has a single outlier with a very large absolute value, the scaling factor for that feature will be dominated by the outlier, leading to a skewed scaling of the remaining data points. Fixes to challenge 1. Consider using a robust scaler like robust scaler or quantile transformer, which are less affected by outliers. Challenge 2. The max abs scaler can perform poorly when the data has a large range of values. Sample use case that resulted in challenge 2. If a feature has a large range of values, the scaling factor will be small for most data points, resulting in a loss of information. Fixes to challenge 2. Consider using a scaler that handles large ranges better, such as min-max scaler or standard scaler. sklearn preprocessing min-max scale. Description. The min-max scaler in Sci-Kit learn is a preprocessing technique used to transform numerical features in a dataset to a specified range, typically between 0 and 1. This scaling is particularly beneficial for algorithms that are sensitive to feature scales, such as k-nearest neighbors, support vector machines, and neural networks. Inputs: array, a numerical array representing the dataset with features to be scaled. Feature range, a tuple specifying the desired range for the transformed features. The default is 0, 1, indicating the scaling to a range between 0 and 1. Outputs: transformed array, the original array with each feature scaled to the specified range. Scalar object, a min-max scalar object that can be used to transform unseen data using the same scaling parameters. Steps: calculate minimum and maximum. The scalar determines the minimum and maximum values for each feature in the input array. Feature scaling for each feature. The scalar applies the following formula to transform the values: scaled value, minimum maximum, minimum new maximum, new minimum. Metrics: scaled range, the scaled range of values for each feature after applying the transformation. Visualization plots: box plot, a box plot visualizing the distribution of features before and after scaling. Scatter plot, a scatter plot comparing the original features against the scaled features. Fine-tune parameters: feature range, this parameter allows you to specify a custom range for the transformed features. For example, you can set it to -1. 1 to scale features to a range between -1 and 1. Uncertainty methods: not applicable. Min-max scalar does not directly incorporate uncertainty methods. However, the scaled data can be used as input to models that handle uncertainty, such as Bayesian neural networks. Challenges and fixes. Challenge 1: sensitive to outliers. Outliers can significantly impact the scaling, especially if the minimum and maximum values are heavily influenced by outliers. Sample use case that resulted in challenge 1: a dataset containing feature values with one extremely high outlier, causing the scaling to be skewed towards the outlier's range. Fixes to challenge 1: robust scalar. Consider using robust scaling methods like robust scalar, which is less affected by outliers. Outlier removal: if outliers are deemed inappropriate for the analysis, remove them before applying min-max scalar. Challenge 2: data leakage. Applying min-max scalar on the entire dataset before splitting into train and test sets can lead to data leakage. Sample use case that resulted in challenge 2: scaling the entire dataset before splitting into training and testing sets, then using the transformed data to train a model. The model might learn the information from the test set due to scaling. Fixes to challenge 2: separate scaling. Apply min-max scalar separately to the training and test sets. Use the scalar fitted on the training set to transform the test set. This ensures that the model is not exposed to the test set information during training. sklearn, preprocessing, normalize. Description: the normalize function in Sci-Kit learns preprocessing module rescales each sample row of a dataset individually to unit norm. This means that the length of each data point vector becomes 1. There are multiple norms available, with the most common being the L1 norm Manhattan distance and the L2 norm Euclidean distance. Inputs: X, a NumPy array or a sparse matrix representing the dataset. Each row corresponds to a sample norm. The norm to use: L1 Manhattan distance or L2 Euclidean distance are the most common options. Default is L2. Axis along which to normalize. 0 means normalize each sample row independently. 1 means normalize each feature column independently. Default is 0. Copy whether to create a copy of the data or perform normalization in place. Default is true. Outputs. X normalized a NumPy array or sparse matrix with the normalized data. Steps. 1. Calculate the norm of each sample row along the specified axis. 2. Divide each element in the sample by the calculated norm. Metrics. None. Normalization itself is not a metric but a data preprocessing step. Visualization plots. None. Normalization typically doesn't lend itself to visualizations. Fine-tune parameters. Norm the type of norm to use for normalization, e.g., L1 or L2. Adjust based on the desired behavior. Access the axis along which to perform normalization. Change to 1 if you need to normalize features independently. Copy set to false if you want to perform in-place normalization to save memory. Uncertainty methods. None. Normalization is a deterministic process and doesn't involve uncertainty. Challenges and fixes. Challenge 1 data with very different scales can cause issues in algorithms like k-nearest neighbors, where distance calculations are important. Sample use case that resulted in challenge 1 applying KNN on data with features like height in centimeters and age in years will give more weight to height due to its larger scale. Fixes to challenge 1 normalize data using normalize to ensure all features contribute equally to distance calculations. Challenge 2 using the wrong norm can lead to undesirable results. Sample use case that resulted in challenge 2 using L2 norm when L1 norm is more appropriate can lead to distortions in data where features with large values are emphasized more. Fixes to challenge 2 choose the norm carefully based on the nature of your data and the algorithm you are using. Consult domain expertise and experiment with different norms if unsure. sklearn, preprocessing, quantile transform. Description. The quantile transform method in Sci-Kit is a data preprocessing technique used to transform features to a uniform or a normal distribution. This transformation ensures that features have the same distribution, regardless of their original distribution. It's especially helpful when dealing with features with skewed distributions or outliers, which can negatively impact certain machine learning algorithms. Inputs. X. This is the input data, typically a NumPy array or pandas data frame. It represents the dataset you want to transform. Output distribution. This parameter specifies the desired output distribution. It can be uniform for a uniform distribution or normal for a normal distribution. Outputs. Xtrans. This is the transformed data, having the specified output distribution uniform or normal. Steps. Rank transformation first. The quantile transform method ranks each feature in the input data X. This assigns a rank to each data point within each feature, indicating its relative position in the distribution. Distribution transformation after ranking. The method transforms these ranks according to the specified output distribution uniform or normal. This means it maps the ranks to values that follow the chosen distribution. Metrics. Distribution similarity. The success of the transformation can be evaluated by comparing distributions of the original features and the transformed features. This can be done visually with histograms or by using statistical tests like the Kolmogorov-Smirnov test. Model performance. The effect of the transformation on the performance of your machine learning model can be measured by comparing its performance on the original data with its performance on transformed data. Visualization plots. Histograms. Histograms of the original features and the transformed features can be plotted to visualize the distribution changes. Box plots can be used to show the central tendency in spread of data before and after the transformation. Fine-tune parameters. N quantiles. This parameter determines the number of quantiles used for ranking and transformation. A higher value can result in a more accurate representation of the original distribution. But it can also be computationally more expensive. Output distribution. This parameter, as mentioned earlier, allows you to choose between a uniform or a normal distribution for the transformed data. Copy. This parameter specifies whether the transformation should be applied to a copy of the data or to the original data. Setting it to true creates a copy, while false modifies the original data. Random state. This parameter is used for reproducibility, especially when using algorithms that rely on random sampling. Uncertainty methods. Bootstrap resampling. This technique involves repeatedly drawing samples with replacement from the original data to create multiple transformed datasets. The variation in the transformed data across these resamples can give you an idea of the uncertainty in the transformation process. Cross-validation. This technique involves splitting the data into multiple folds and applying the transformation to each fold separately. The difference in the transformed data across the folds can provide a measure of uncertainty. Challenges and fixes. Challenge 1. Description overfitting to the data. If the n quantiles parameter is set too high, the transformation can become too sensitive to the specific values in the training data. This can lead to overfitting, where the model performs well on the training data but poorly on new, unseen data. Sample use case. When transforming data for a fraud detection model, using a very high n quantiles might capture specific patterns in the training data that are not generalizable to real-world fraud cases, leading to poor performance on unseen data. Fixes. Lower the value of n quantiles to reduce sensitivity to the training data. Use cross-validation techniques to evaluate the model's performance on unseen data and adjust the n quantiles parameter accordingly. Challenge 2. Description handling of outliers. The quantile transform can be sensitive to outliers, as they can significantly influence the ranking and transformation process. This can distort the resulting distribution, leading to inaccurate transformation. Sample use case. In a medical dataset with blood pressure readings, a single very high blood pressure value could significantly impact the transformation of the entire feature, leading to an inaccurate representation of the blood pressure distribution. Fixes. Remove outliers from the data before applying the transformation. Use a robust outlier detection method, like the IQR interquartile range method, to identify and remove outliers. Consider using a different preprocessing method, like standardization or normalization, that is less sensitive to outliers. sklearn, preprocessing, robust scale. Description. Robust scaler removes the median and scales the data according to the quantile range IQR. Interquartile range. Inputs. X. The data to be scaled. With centering Boolean. Whether to center the data before scaling. With scaling Boolean. Whether to scale the data after centering. Quantile range tuple of floats. The quantile range to use for scaling. Defaults to 25.0, 75.0, which corresponds to the IQR. Copy Boolean. Whether to copy X or perform in place scaling. Outputs. X scaled the scaled data. X the original data. Steps. Centering subtracts the median from the data. Scaling divides the data by the quantile range. Metrics. Range. The range of the scaled data. Fine-tune parameters. With centering, set this to false if you do not want to center the data. With scaling, set this to false if you do not want to scale the data. Quantile range, change this to a different tuple of floats to use a different quantile range for scaling. Challenges and fixes. Challenge 1: the scaled data may have a different range than the original data. Sample use case that resulted in challenge 1: the original data has a range of 0 to 100. But the scaled data has a range of -1 to 1. Fixes to challenge 1: rescale the data to the original range. Challenge 2: the scaled data may not be normally distributed. Sample use case that resulted in challenge 2: the original data is skewed. And the scaled data is also skewed. Fixes to challenge 2: transform the data to a normal distribution before scaling. Sklearn, preprocessing, scale. Description. The scale function in Sci-Kit Learn's preprocessing module is a utility that standardizes features by centering them at 0 and scaling them to unit variance. This process is often referred to as Z-score normalization. Standardization is crucial in many machine learning algorithms as it can improve performance and stability, especially when features have different scales or units. Inputs. X, a NumPy array or pandas data frame containing the data to be scaled. Each column represents a feature. Axis optional, the axis along which to calculate the mean and standard deviation. 0, calculate statistics for each feature across all samples. 1, calculate statistics for each sample across all features. Outputs. X, scaled, the scaled array, where each feature has a mean of 0 and a standard deviation of 1. The original shape of the input array is preserved. Steps. Calculate the mean of each feature or sample depending on the specified axis. Calculate the standard deviation of each feature or sample depending on the specified axis. For each feature or sample, subtract the mean and then divide by the standard deviation. Metrics. Mean, the average value of each feature or sample after scaling. It should be close to 0. Standard deviation, the spread of values for each feature or sample after scaling. It should be close to 1. Visualization plots. Histograms, plot histograms of each feature before and after scaling to visually observe the shift in distribution and the reduction of variance. Fine-tune parameters. Axis, this parameter controls the direction of standardization. 0, standardize features, making each feature have a mean of 0 and a standard deviation of 1. 1, standardize samples, making each sample have a mean of 0 and a standard deviation of 1. Uncertainty methods. None, the scale function itself does not directly provide uncertainty estimates. If needed, uncertainty analysis could be performed separately using other methods like bootstrapping or Bayesian approaches. Challenges and fixes. Challenge 1: outliers, extreme values in the data can significantly impact the calculation of mean and standard deviation, potentially leading to inaccurate scaling. Sample use case that resulted in challenge 1: a dataset containing the heights of students, where one student is significantly taller than the rest due to a measurement error. This outlier could skew the mean and standard deviation, leading to incorrect scaling for the other students. Fixes to challenge 1. Robust scaling. Consider using robust scaling methods like sklearn, preprocessing, robust scaler that are less affected by outliers. Outlier detection and removal. Identify and remove outliers before scaling. But be cautious as removing data can lead to information loss. Challenge 2: data with 0 variance. Features with 0 variance, all values are the same, cannot be scaled using the scale function. Sample use case that resulted in challenge 2, a dataset containing information about a specific type of car. The make feature has the same value for all cars, resulting in 0 variance. Fixes to challenge 2. Feature selection: remove constant features before scaling. Feature encoding: encode constant features using a one-hot encoding scheme to create binary features. sklearn preprocessing power transform. Description: Power transformer applies a power transform to each feature of the input data, making the distribution closer to a normal distribution. It's particularly useful for dealing with skewed data and enhancing the performance of models that assume normality. Inputs: X, an array-like input data containing numerical features. It's typically a 2D array where rows represent instances and columns represent features. Method: the power transform method to apply. It can be Yo-Johnson default or box-cox. Yo-Johnson, a more general transformation that can handle both positive and negative values. Box-cox, applicable only to positive values. Outputs: X transformed, the transformed array-like data where each feature has a distribution closer to normal. Lambdas, an array containing the optimal power transform parameters for each feature. If method is set to Yo-Johnson. Steps: Data preparation: the input data is transformed to a NumPy array if it's not already one. Power transformation: the selected power transform method Yo-Johnson or box-cox is applied to each feature, adjusting the distribution to approximate normality. Return transformed data: the transformed data and optionally the power transform parameters are returned. Metrics: Kolmogorov-Smirnov test measures the goodness of fit of the transformed distribution to a normal distribution. Skewness and kurtosis measures of the shape of the distribution. Transformed data should have reduced skewness and kurtosis, indicating a more normal distribution. Visualization plots: histograms visualize the distribution of each feature before and after the power transformation. To assess the improvement, QQ plots compare the quantiles of the transformed distribution to the quantiles of a standard normal distribution, providing a visual assessment of normality. Fine-tune parameters. Method: choose Yo-Johnson for a more general transformation or box-cox for positive values only. Standardize: if set to true default, the data will be standardized before applying the transformation. Standardization helps ensure consistent scaling across features. Copy: if set to true default, the input data is copied before transformation. If false, the transformation is performed in place. Uncertainty methods. Bootstrapping: resample the data with replacement multiple times and apply the power transform to each sample. The variability in the resulting transformations provides an estimate of uncertainty. Challenges and fixes. Challenge 1: data with very small or large values can cause numerical instability during a transformation. Sample use case: a feature with values ranging from 10 to 10 to 10 10. Fixes. Scale the data: apply a scaling method like min-max scaler to bring the values into a more manageable range before transformation. Consider alternative methods if the data has extreme values and the power transform doesn't work well. Try other methods like logarithmic transformation or a robust scaler. Challenge 2: the power transform may not be effective for data with multiple modes. Multimodal distributions. Sample use case: a feature representing customer age with two distinct peaks, e.g., young adults and older adults. Fixes. Data segmentation: segment the data based on the modes and apply separate transformations to each segment. Alternative transformations: experiment with different transformations. such as logarithmic transformation or a non-parametric transformation.